So for guys who have not met me before, I'm Feeding, and I've been kind of programming since, I don't know, 11 years ago. But I recently got into games a couple of years ago, and actually I only started using Unity about 6 months ago. So I'm not a Unity expert by any means, but the purpose of this talk is to show you guys kind of challenges and ways of solving problems I've faced when trying to create random procedural content in Unity. So let's get started. Okay, so kind of two types of procedure generation when people talk about procedure generation in games. First is kind of the outdoor procedural stuff, so games like Minecraft and Terraria, that kind of thing. People normally talk about Perlin noise, fractals, generating height maps and biomes and things like that. So that's kind of not really the focus of today's talk. My game is more on dynamically instantiated indoor levels, so games like roguelikes and dungeon crawlers. You can apply the same techniques to like office complexes and maybe like sci-fi stuff as well, like spaceship interiors, that kind of thing. So yeah, if you want to know something about outdoor stuff, then don't ask me any questions. Okay, yeah, most of the techniques today I'm going to talk about require Unity Pro, mainly because Unity Pro includes a lot of features that allow you to really optimize the game, really get the most out of performance you can. So it includes things like occlusion culling, nav meshes, static batching, that kind of thing, and also the memory profile as well. It's a really, really helpful tool to kind of find out where bottlenecks in code are and really dig down without the guesswork involved. And the second best thing, or maybe the first best thing about Unity Pro is that you get a dark skin, so that's awesome. It's still so much better, and it's actually scientifically proven to make your code run faster as well, but that may not be true. So my game that I've been working on for the past 6 months is called Tiny Keep, and it's basically a procedurally generated dungeon crawling game. Some people call it roguelikes. I'd like to think more of it as a roguelike-like. It's kind of doesn't really fit the definition of being a roguelike. It's kind of real-time. It's not turn-based, but it has some roguelike features like random generation and a little bit of permanent death as well. So, and that got kickstarted last year at I think it was May or June. So that was successful, and I've been working on it ever since. So it's due to be released this time September. So I'll just quickly show you guys a video of, really quick video of what it's all about. This is the latest development teaser that I released last week actually. So I'll just quickly just run through the game in a couple of minutes, just to show the kind of stuff that I'm doing, and talk about how I actually implemented it in Unity. I've got a really bad laptop, so I'm going to maybe show it down too low. It's procedurally loading based on a seed. I've just selected a random seed, and every time you play, if you input the same seed, then it would generate the same level. So the main feature of the game is everything's kind of generated randomly. Everything is physics enabled, so most of the stuff you can see is rigid bodies, so you can kind of knock over lights. All the lights are dynamic point lights. You've got real-time shadows coming off from the lantern at your belt there. Torches are point lights, you're dynamically instantiate point lights. You've got particle effects on there as well. Monsters have adaptive AI, so obviously they, because the level is generated randomly, they won't have any kind of hard code. They can have mesh pathfinding in there, so it's all very much reactive to kind of surroundings, the player, furniture as well. So obviously you can move tables around, and they will react according. So they'll jump over stuff that's there. If you're not in their line of sight, they'll still be able to kind of chase you around the level. So even if you kind of hide behind this corner here, they'll still be able to find you. So that's kind of like a mixture of kind of pathfinding and some sensors, triggers as well. Now, I'll quit that. So that's basically the game as it stands at the minute. It's still work in progress, so obviously not everything's implemented, but hopefully that will give you an idea of the kind of project that I'm trying to create. So there's kind of 3 steps required to create a random generated level. And first is to have an algorithm to generate a layout. So when I talk about layout, I'm talking about rooms and corridors, where they're going to be, what size the rooms are, what shape the rooms are going to be, where the corridors, how they're going to be connected. So we need to design an algorithm to do that. Once the layout is generated, you need to transform the layout into kind of usable level data. So in this case, the game is very much tile-based, so each of the corners and walls and floor tiles all occupy space, coordinates, if you like, so say X and Y coordinates in a level. So there's the level kind of structure is, because there's only one floor, it's really very much 2D game rather than 3D game, and you can jump across tables and stuff, but you know, if you talk about abstractly, it's kind of a very much 2D game. So the level data is really simple to do. Once you've got the level data, then you can actually attach your game objects to the scene. So the difference between this kind of game and a normal Unity game is, in Unity you would normally have a workflow where you go into Unity, you go to the scene, create a new scene, create your levels from there, drag and drop your assets onto the stage, add your colliders, generate your nav mesh, that kind of thing, and then off you go, you've got a game. With TinyKeep, it's a little bit different, because if you actually go into Unity, you go into the main scene, there's only one scene, and this is pretty much it. There's actually nothing there. You've got your main game object here, it's actually an empty game object, and you've got your script here, which is the entry point to the game. So if you're into C++, then that's pretty much like your main function, same kind of thing. You've got your cameras, so you've got your chase camera, clear, which just clears the background, you've got your GUI camera, so that's kind of the usual stuff. Singletons doesn't actually have anything in there until you actually start the game. Your game world is actually a container where all of the different pieces, so the dungeon walls, floors, corners, doors, that kind of thing, get added at one time. But at this time there's actually nothing in there apart from a floor and a ceiling collider, which are 2 colliders, and they'll always be in the game. And then just a temporary game object where I put random stuff during when it's experimenting stuff, but that's not actually to be there. So it's a little bit different to most games where you have a level kind of built in to the editor and you're able to see visually exactly what's going on. So it does require a little bit of imagination and constant kind of, you write your code in C#, you write your dungeon generation there, you press play. It doesn't quite look quite right, you have to press stop, go back to your code, and then kind of repeat that kind of workflow. So it is a lot more work than what you might normally do in Unity. I call this kind of random generated fallacy, where a lot of kind of developers think that, I'm going to make my game randomly CD generated because I can't be bothered to do level design. But actually it makes everything so much harder once you start doing the CD generation. You can see how that's right. Okay, so to start from the beginning, I'm not going to go through this too much detail because it's not strictly Unity related, but it just helps set the context for what I'm trying to do. So to create your layout, your rooms and corridors, traditionally in a roguelike game, if you go to a website like roguebasin.com, then there's plenty of different algorithms you can use to generate your dungeons. I think normally you'd have something like tree-like structure, so maybe you start off with a room like that, and maybe you decide to build a corridor off to the north, So maybe you have a few corridors up here like that, and then you have another room, and then maybe you have a corridor that's branching off that original one. Maybe a corridor come off here, and another room here. So that's kind of how most kind of roguelites do it, and just as a starting point, and then they kind of tweak and change things. I found that the problem with this kind of approach is that it's really difficult to get loops in the layout. So say if you've got your dungeon layout like this and you wanted this to actually loop back to this one, so you have a little bit of circle here. That's actually really hard to do because you might have a corridor that kind of winds around all the way around here, and then you want it looping around here, and then it's non-trivial to implement. You've got to do some pathfinding to see if it overlaps any other existing corridors, or find out if other rooms in the way. And it's also really difficult to get a consistent number of rooms in your layout as well. So say if you always wanted between 40 and 50 rooms in a dungeon, without really hard coding, kind of edge cases and adding a lot of heuristics in there, it's really hard to get a consistent number of rooms in your level. And also sometimes you end up with something that looks really ugly as well. And, like this one, we have a corridor that goes around. Actually, there's nothing to turn. So what we've done for the time keep is spent 3 or 4 months working on a new kind of algorithm that I've started to use, and it's a different kind of approach. You start with the number of rooms that you want it to do. And I'll just show you a quick visualization of that. And you just keep refreshing them, and it will generate a new random seed every time. So I've got a little video of that showing, so I can just scrub through and show you step by step exactly what's going on. So I start off with a target number of rectangles to spawn. So I've selected 150 here. That doesn't mean 150 rooms, it's just an arbitrary number. But I know that 150 room rectangles will always yield me, say, between 10 and 50 rooms in the level. And what we do is we just spawn rectangles randomly in the centre of the screen. It doesn't matter if they overlap. And the sizes of the rectangles are based on just basically picking a random number between, say, 4 and 10 or something like that. So you can get rectangles or squares. There's a limit to the ratio between the width and the height of each rectangle as well, so you don't get really skinny rectangles, and you don't get really skinny ones. So you want kind of more of a squarish shape. So you do that. So generate about 150 of those. What I should say is, instead of using a normal random function, which brings back equal chance of getting between 0 and 1, I'm actually using normal distribution. So it's more likely that you get 0 rather than 1. So if I normalize this curve to 0 and 1, so you have 0 here, and 1 here, and -1 here, you're more likely to get numbers that are smaller rather than larger. So what you end up with is rectangles that are, you get more rectangles that are small and less rectangles that are large. And the reason that I'll do this, I'll explain in the next stage. Okay, so we've got your overlapping rectangles here. Now we wanted to push them apart so that they don't overlap anymore. So if you've ever worked in AI, you might have looked at some steering behaviours. And part of steering behaviours is separation. So you might have a few monsters grouped together, but you don't want them to converge into one point. You want them to separate out, and if you don't have a physics engine, you can still use separation behaviour to make sure they don't touch. So I'm using the same kind of principle here to push apart the rectangles. It's the technique I'm using is called inverse square law. So basically, if you've got 3 overlapping rectangles here, you work out the vector between, say, this rectangle and this one here, and the magnitude of the vector is the dotted line, and the direction that you want this square to move is probably this way. But that's actually, if you go and compare these two, then you probably want to move it the other direction. So the resulting vector would be going up, And the strength of the potion is a coefficient. In my case, I'm using 1, but you can scale that up and down depending on how strong you want your potion to be, over magnitude squared, and the magnitude is the dotted line, the length of that line. So that's a really common algorithm for using in separation AI, and actually in real life it's I think it's applied in magnetic propulsion as well. So if you have two magnets that repair each other, then they also follow in the square law. I mean, I'm not a physics expert, but that's pretty much what I read in my AI books. So after you've got all your rectangles separated and guarantee that none are overlapping. There might be a couple more overlapping, but just remove those. I think in this case you're pretty, no overlaps there. And then you just pick the rooms based on threshold. So say any square that has a width or a height greater than 7, make that a room. So now we've got a list of rooms. So we've got 19 rooms here. We want to connect them together with corridors. So what we do is we generate a graph, and the algorithm I'm using to do that is called, well, I can't pronounce the D word, Delaunay or something like that anyway, triangulation. And you can kind of read this up on Wikipedia, what the algorithm is. I didn't actually spend time actually understanding what the algorithm does, but just implement it in code. It's pretty simple. But what it seems to do is triangulate. So for a list of vertices, say each of these vertices are center points for each room, but create edges connecting all of the rooms together in such a way that none of the edges overlap. So you won't get an edge going from say here to here because they'll be overlapping with this one. So that ensures that every vertex is connected. But if you actually leave this as it is, obviously we don't want our dungeon to be looking like this. It's unless you want, I don't know, the feel of driving through Milton Keynes or something. And, every other dungeon, every other room is connected to every other, and it's it's a bit of a confusing layout. So what we do is we take this graph and we process it further using minimal spanning tree. So if you imagine these grey lines here were from the original triangulation, minimum spanning tree would generate a subgraph of a triangulated graph that would guarantee all vertices are connected to the graph and no more. So there would be the minimum number of edges needed to connect all vertices together. So what that does is that guarantees that your dungeon will always be solvable. So if you start from, say, here and your ending's here, there will always be a guaranteed path from beginning to end. Now this is kind of the other extreme from triangulation because, again, we don't have loops. So if you have a minimum spanning trees, because it's a tree-like structure, you don't have a variety in your dungeon. So if you say you wanted to go to this room and then you wanted to go back here, you'd have to take the same path again. It might be nice to have another corridor going down here. So the simple solution to that is incorporate a small percentage of the original graph into this one. So maybe you take 15 to 20% of the triangulated graph and say that one there, that one there, that one there, but not all of them. Otherwise, it will just make the dungeon really confusing to navigate. So that's pretty much what we've done. So you can see here, the bold line is the minimal spanning tree, and the green kind of thin line here is the excess edges from the previous triangulated graph. So we've kind of really got a nice layout now, and what we need to do finally is to actually convert this graph, as I mean it's just vertices and edges, into actual corridors. And it's really simple. I'm not doing anything too clever. All I'm doing is for this edge here, I want it to make a corridor. I'll just do an L shape. So maybe either up and right or right and up. I just choose that randomly. So you get corridors there. And then what we do is draw a bounding box around each of the lines. And then any of the previous rectangle cells that were intersect with the bounding box get converted into corridors. So they end up something like that. So I think it looks quite nice. The benefit for this is because of the different size rectangles that you've got here, you don't have completely straight corridors. You get almost a little bit of twisty walls here and that kind of thing. You can always, if you wanted to get a little bit more variety, you can always instead of just an L shape, maybe do 3 sections to the line, or maybe 4 sections, and get a bit more windy dungeon. But for Tiny Keep, we wanted to have a more of a kind of less windy route. So I think for this, it's created a really great level already. You can see that, say the starting room was here, and the end room was this one. You'd have some multiple routes there. You've got a loop around here, and you've got some extra rooms. Maybe you've got this room here which has put your treasure or your boss mob here, or that kind of thing. So there's loads of different ways you can kind of transform this into a level. And then after that, you just do other stuff like add doors and keys and locks and that kind of thing. But I won't go into that to too much detail, because probably should get onto Unity stuff now, otherwise Joe will turn it off and have to talk about Unity, so we'll do that. Oh yeah, the minimum spanning tree algorithm I'm using is called Grimm's algorithm. It's the simplest and fastest one to implement, so that's on Wikipedia as well. If you want to get the slides, by the way, I'll be posting them up on Twitter at some point as well, so if you guys follow the NCR and UEG, hopefully you'll be using that. So after you've got the layout, convert that to level data, which is really simple. It's a 2-dimensional array of objects, and each tile will say that's a floor, corner, or wall, or whatever. So we transform the layout into that, and then from there we can start putting our game objects down into the scene. So like I said, for a normal Unity game, you probably do this in editor time. So you'd say you'd have some floor tile here, just drag and drop that, make sure that's on normal, just turn right off. So you might copy that. You might even actually have if you're having a room with, say, a 6x6 floor, you might even have a whole plane there, and then you can tile the texture so that you reduce the number of bodies. But for my case, we're not using the editor, we're doing everything in code. So the easiest way to do that is to have everything in prefabs. So in my resources folder, Tiny Keep prefabs, all of these are actually prefabs, or prefabricated objects. So if we put a file structure here, you can see that all of these have been prefabbed. And in code, all you have to do is go resources.load, the path to prefab, and now it will give you a game object back, and then you can get your game world container, and then do add child in your prefab, and that will add. So from the level data, you basically just iterate through each of these columns and rows all the way to the end, get the correct prefab, add them to your scene, and then you've got your level. So it sounds pretty easy, but there's quite a few challenges from there. So if you imagine a medium-sized dungeon, or maybe even a small-sized dungeon, you've got 100 by 100 grid. So that's potentially 10,000 tiles, which equals 10,000 game objects. Now if you imagine each tile has its own collider, it might have a torch connected to the wall, so particle systems, dynamic lights. That's potentially 10,000 of those things. And then if you've got furniture in each room, then that's potentially more rigid bodies as well. So if you just add all of these objects to the scene, and then start to run a game, you're going to get a really, really bad frame rate. So you need to kind of fix that. What I wanted to do with Tiny Keep is to have everything dynamic. So point lights, for example, for torches and grazers, cast real-time shadows. So it's a Unity Pro feature. You can have as many point lights as you want, each of them casting shadows. So you can imagine the overhead that would cause as well. And obviously rigid bodies everywhere from furniture. So part of the game mechanics is to be able to push tables around, chairs, block doors, and so prevent monsters from coming in, that kind of thing. So if you have all of these rigid bodies around, you can imagine the strain that causes the physics engine when you start going. And also if you're spawning monsters and you've got AI everywhere, because the level's randomly generated, you can't use things like nav meshes to bake in your pathfinding, so you're going to have to do dynamic pathfinding as well. And then if you have furniture that can move around, the doors are open and closed, then you kind of have to write that yourself. So those are pretty big challenges that we have to solve. The main one being thousands of game objects. I mean, if you just put everything into one thing, you're obviously not going to get a game that runs fast. So if you go to Unity website, manual, and then go into the manual, and scroll down to, I think it's called performance optimization. No? Optimizing graphics performance. So what this gives you is a list of all the different things that Unity recommends that you should follow, best practices when you're creating Unity levels. So I'll just quickly go through a smaller version of that. So the first thing is very, very obvious, is reduce the number of draw calls. So minimize the number of materials, and if you've got Unity Pro, then do static batching. Static batching means that if you've got static elements in your level, for example, floor tiles or walls and corners that will never ever change during that playtime, then you can go into Unity and say mark that as static. And what that does is, for all the static objects that are marked static and they have the same material, the Unity renderer will render the entire thing in one batch. And it's a lot better than dynamic batching because it takes the guesswork out of that. So if you can get Unity Pro, and static batching is a really, really good kind of technique to use. So that reduces, drastically reduces the number of draw calls. Reduce the number of colliders and rigid bodies. Obviously, the more colliders and rigid bodies you have, then the more strain that we have in the physics engine. So in particular, colliders, if you've marked them as static as well, and if you have a rigid body on there, sorry, if you have a collider that doesn't move, then don't add a rigid body to it, and that'll be marked as a static collider. If you have a collider that does move, make sure it's got a rigid body on there, otherwise it will keep refreshing the collision detection world space. So every time you move the object, you have to refresh the entire collision detection structure. So definitely reduce the number of colliders. Use a single directional light and use forward rendering for it. So it's great for, say, outdoor levels where you've got one single light source, which is the sun. So that's kind of what Unity says, if you're targeting mobiles, is to use only a single directional light. And then for point lights, for example, the torches like I had before, then you want to bake them using light mapping. It's what it does is it takes a point light, works out, calculates the lighting on each of the elements around it, bakes that into the texture, and then so when you actually run the game, it doesn't have to calculate the lighting for every frame. And then if you've got Unity Pro, then with light probes you can have dynamic lighting in the character, because obviously if you have baked point lights that have been light mapped, your character will still need realistic lighting as they move around the lights. So with light probes you can strategically place lights on the scene that will only affect your characters. So that's really helpful as well. And use occlusion culling. Occlusion culling is pretty interesting. Just quickly. So say you've got a character here, and this field of view is something like that, maybe 60 degrees. In front of you you've got a lot of crates. To the side you've got crates as well. So what Unity does is automatically, because of your camera, doesn't render these objects because they're outside the camera custom. So it'll render these because you can see it. But what Unity will also do is render the objects behind it, even though you can't see them because they are occluded by these barrels in front. It will still calculate the draw calls for these three objects here, unless you use occlusion culling. So what occlusion culling allows you to do is, in the editor time, bake in positions of the objects so that when you play it and you come into contact with them, it won't actually render these. So that's really helpful. So you can imagine for a dungeon crawling game, you've got a character here inside a room, and you've got another room behind here, another room behind there, and you can probably go on forever. So you don't want to render these rooms, so occlusion culling will really help with that. And obviously use nav mesh agents. So if you bake your nav mesh at editor time, then your agents don't have to calculate pathfinding dynamically. So that's what I've got a Unity way, and how Unity recommend best practices for creating all Unity games. Unfortunately, because I'm now procedurally generating TinyKeep, quite a few of these are unavailable to us. So I can't really reduce the number of colliders and rigid bodies because, like I said, I want all the furniture to be as dynamic as possible. I want that to be part of the game mechanics. I don't really want static furniture. If we're generating dynamic walls and floors, each floor tile will have its own collider, each wall will have its own collider. You could be a bit clever about it and say if you have a square or say 6x6 floor tiles, then actually only use one collider there, and same with the walls, but it's not really trivial thing to implement, especially if you've got really varied dungeons. So that's not, you can reduce the number, but there's only a limited amount that you can do. Single directional light, well, there's no outdoor lights in dungeons, so we don't use that. But there's a lot of point lights that we do use. So the torches and the blazes and that kind of thing. But like I said, for Unity, I want every light there to have cast shadows and to be able to be turned on and off, so we're able to chuck water on some stuff or knock torches over. Monsters might decide to blow lights out, that kind of thing. So we can't really bake point lights in, so we can't really use light mapping or light probes. So we can't really do that either. Occlusion culling, that's great. Allows you to say what things aren't rendered based on what's been included. However, occlusion culling is only available to Unity in editor time, not in runtime. So when you're procedurally generating at that time, you don't know, you don't have a predefined level where you can bake occlusion culling. So, and there's no way of calling the occlusion culling and baking it during runtime. So again, that's not really available to us as well. Nav mesh agents, really useful for AI. If you're creating a dynamically generated dungeon, nav meshes have to be baked in at editor time, so you can't do that. So pretty much screwed if you're creating a randomly generated game. So what are the workarounds or solutions? So at this point, as you can imagine, I've just freshly bought Unity Pro for 700 quid or whatever it was, or your or subscription, say, I can't remember how much a subscription was. And then you actually come to writing a game and you think, shit, I can't actually make my game without it running really slow. So what's the solution? So I'm not saying this is the perfect solution for all types of games, but I found it worked for mine. And not to say that Unity in any way is incapable of doing really, really great games. It's just not designed for procedurally generated games. So the first thing to do, really, really quick win, change camera angle. So instead of having a behind character camera, move it so it's kind of more bird's eye view. And what that does is obviously, rooms that aren't in view of the camera around the character, so they don't get rendered. So already that reduces the amount of rendering that the game has to do. So that's a massive win, reduces your number of calculations for rendering and increases your frame rate quite a lot. I think for this type of game as well, it really helps. It's kind of got more of an old school feel. You want it to be able to see behind your character as well as in front. It's a less kind of realistic game, so if you're thinking of roguelikes and kind of classic Baldur's Gate, that kind of thing, you're able to see all the costs around you of your character. So the camera angle that we've chosen works for the game mechanics that we want, but also helps us render as the least amount of geometry as possible. So that's a really, really, really quick thing to do. Static batching in code. So if you remember from the previous slide, I always recommend using static batching if you have geometry in your level that never changes. So the only caveat for that is if you dynamically instantiate a prefab and then add it to your scene in runtime, the static checkbox doesn't actually work. So say in my prefab here I've got an arch. So if I say, okay, yeah, the arch doesn't change, that's always there, I'll mark that as static. And then you'd expect that once you instantiate the prefab, add it to your scene, that'll just work. Unity will recognise that as a static object, batch it in audio, of course, with all the other parts of the level that share the same material. Actually, it doesn't. It completely ignores that. It only works if you have an arch already in your level, and then you set that as static, and then that will be marked as static. So what you have to do to work around this is to mark that static in code.
Also submit a bug report to Unity.
Sorry?
Also submit a bug report.
It's not actually a bug report, it's It's actually a bug. It's actually is in the Unity manual, but it's really, really easy to miss. And because if you're actually navigating a prefab, they probably really shouldn't put that there. You know. But it does say in the documentation to use the static patching class in C# and do it in code if you're instantiating dynamically. So it's really easy after you've added everything to the level. So I'll just look at my rendering class here. So this is my game world container. So at runtime I'm adding everything to this game object. So I'm adding all my floors, walls, contents of the room, junk, like bits of bone, broken rocks and that kind of thing. And once everything's been added to the container, we use a static function called static patching t.combine, and then you pass in the container, and that will, I think that will recursively mark all our children of that container as static, and then it will work. So it's just one thing to bear in mind if you're thinking of doing. Oh, that looks really bad. Okay, so the main problem that I found is the amount of physics calculations that Unity has to do when you're generating random content. For example, we've got 50 rooms, and each room has at least 5 tables, or a cage, or a torch, that kind of thing. And they're all rigid bodies, so they're all knocked over, pushed around. And if you add all of those to the scene, there's a kind of a brief moment of, say, 5 seconds when you start the game, where the physics engine is trying to settle all of these rigid bodies, so it starts shaking around, and frame rate will go down to like 5 frames per second, and you know, it's really bad frame rate. I mean, once the objects themselves have actually stopped moving and they've settled down, and then the physics engine marks it as being asleep, it's still not as fast as what you want it to be. So what I've done is almost kind of rewritten or rewrote a kind of an inclusion culling solution. Not really, but it's basically recursively enable and disable objects around you by proximity. So if you imagine your character in a room and you've got a radius of say 5 units, and any object within that radius will be enabled, and any object outside of it will be disabled. And by what I mean by enabling and disabling, I'm turning on and off mesh renderers, I'm turning on and off rigid body physics, I'm turning off on lights, particle systems. Some particle systems use the physics engine as well, so you want to reduce that as much as possible. But it's one thing that do not enable or disable colliders. As I said before, if you change static colliders and turn them off and on, collision detection will have to refresh. So if you do that every frame, then you can get really bad frame rate as well. So I can really quickly show you how the activator works by reducing radius. So at a minute it's 10 units, and you can't really see it happening in normal game because a radius of 10 is outside the size of the camera that you can see. But I'll say if I reduce that down to 2. And actually let's get rid of the skeletons as well, so not the skeletons. So maximum some more. See here, kind of radius 2 units, so that's 2 floor tiles. So things that are enabled and disabled as you walk through them. So actually, you know, nothing's rendered, physics completely turned off, so only things in your immediate proximity get turned on. So you can kind of see that happening. So yeah, actually, if you go into a room where there's a bit more stuff, you can kind of see objects. See those barrels that just jumped in. Basically, the physics of the barrels are only just get turned on just as you walk into the room. And if you walk away, they get turned off. So it's effectively what I'm doing for the entire game, except I'm setting the radius to 10 so you can't actually see it happening. So what it does is that I only have the active objects there in the character, so you're not having to calculate a million things in the entire level. Same things happen with monsters, but what you can do is have monsters not affected by the activator, and you can have, so you can still activate and deactivate, say, colliders and mesh and the animated skeletons and the animated bricks and that kind of thing. So you can still enable the save of those, but if you have the AI running, then they can still navigate around the dungeon even if you're not activated them. So you can still have independent monsters moving around the dungeon even if you're not activated. So that's pretty much it, and that alone is it's greatly improved the speed of the game as well. So it'd be nice maybe in future if Unity would have maybe a component built in where you can say this object is activated only when you move away. That would be cool. So there's one last thing I'm going to talk about, and that's AI. So first of all, if you've got, say, 50 monsters navigating around a dungeon, and there's an AI routine running the script, is it really necessary to have 60 frames a second of AI? My answer is no. I've done some testing, and actually, if I reduce the AI down to 15 frames a second, behavior is still intelligent. You can't actually tell from the player's perspective, but you free up a lot of CPU cycles. So obviously, things like rendering physics, you want to keep at 60 frames per second. You want 60 frames. You want nice smooth frame rate graphics, but for AI, because the player can't notice it. I mean, if you think about it, if you're moving around the street, you're not really taking notice of everything around you. 60 frames per second, so it's the same kind of principle. You can also reduce the frame rate the further away you are from monsters as well. So, say you've got a skeleton that's in a room like a mile away, you don't want the priority to be with him. You want more AI time for stuff that's closer to you. So that really helps as well with improving speed. And also, final thing I want to talk about is normal Unity games use something called nav meshes, which you have a level that's been defined in Unity. You bake your nav mesh, and then you can set up nav mesh agents, and they can navigate around your level. And obviously, like I said before, if you have randomly generated levels, you can't use nav meshes. So you're limited to pathfinding, dynamic pathfinding, so say something like A-Start. But what I found in TimeCube is that pathfinding actually is not really that necessary. If you imagine you're coming up to a boss or a skeleton and you're about to fight them, they're not going to suddenly try and calculate the shortest path to you based on what you can see. It will just run towards you and then maybe strafe left and right based on what's in front of it. If there's something in front of it, it might jump over it or that kind of thing. So it's all completely reactive. So what I've done is just really quickly show you how I've done that. And I use something called breadcrumbs. Turn on the mesh. You can assume that the skeletons have no prior knowledge of the level, they're not using pathfinding, they're not calculating shortest paths. They can only see you if they're in their line of sight, and they'll try and follow you that way and dodge obstacles on the way. So I've got breadcrumbs here. So I'm just going to up the radius. So it's got me in his line of sight. Actually, if I move away so he can't see me anymore, he will actually follow the breadcrumbs I'm leaving behind. Breadcrumbs only kind of stay there for a few seconds. But it kind of gives the impression that there's some kind of really clever pathfinding going on.
There is, I think.
And this really is kind of one of the few ways that you can get realistic pathfinding without actually using it in a randomly generated environment. So I'm going to hide here. Oh, and I also have, so say this is my monster here. I've got some triggers left and right, so if there's anything in that one's left, it will start right, and right start left. Trigger here, anything in front of it, it will jump over it. So if you imagine a robot with sensors and kind of infrared detectors, it will do kind of the same thing. So, and that I found is a lot quicker for the computer to calculate than planning something like pathfinding every frame. And that's pretty much it. So I wouldn't say that that's the only way of doing a game like this, but I found that it works automatically. And that's pretty much it. So if you want to find out more about the game, go to feeling.com, use the Bluebird thing and follow me at V6, or if you're old school, then email me at Jess if you want to find out more. So yeah, I'd like to open up to any questions if anyone wants.
We've first of all a massive round of applause for
if you've got a tile-based world and it's on one level, would it be more or less efficient to use one giant plane spanning the whole thing as your collider, and then having each individual tile not have a collider?
That's actually what happened. So, so I've got 4 floor collider here in the world itself, and the reason that is basically the only object in the world that's already there, and I just in-game. So during runtime, I'll just extend that so that it matches the size of the level that's generated. But that's the only time I'm using a single collider for my level. For the walls and corners and doors and that kind of thing, then each tile has its own collider, because I find it is non-trivial, really time-consuming to build a system where say you've got a long stretch of walls and kind of collider there, and you kind of get into really weird edge cases and that kind of thing. So I just wanted to go for something that was really quick to implement.
Yeah. If you're procedurally generating a dungeon, surely you could also procedurally generate a simplified nav mesh to try and help with navigation and things like that.
I didn't realise that was possible to define a nav mesh in runtime.
You can just develop or define any kind of mesh itself,
right, and
then use that for actual collision detection and things like that to try and simplify or speed things up.
Okay. I have not tried that at all. But if you want to talk about it later, then explain it to me, because I really don't understand.